Thank you. Today, I'm pretty happy to be presenting a project that's been sitting on a little bit on the back burner with COVID and everything, but finally we get to bring it up. And it's a project regarding circular economy, cascading, and all the ideas of multifunctionality, and with a specific focus on the quality indicator. It's a project we did at the LCA and in collaboration with the CIRCEL. So this is the outline of the presentation. I just don't want to spend too much time on it since it's straightforward. So materials and products often follow this linear make, use, dispose paradigm where we just extract resources, we use them, and we just get rid of them. But we can also scratch that because sometimes we shift to a circular and cascading paradigm where we repair products, we reuse them, we redistribute them, we will extract components or refurbish them, or even try and get energy out of them. And this gives rise to challenges when we're going to do the LCA of this, because these multiple cycles induce multifunctionality. And we have also the issue of upcycling and downcycling of our materials, which will actually induce the idea that not all cycles are equal between each other. So multifunctionality induced by these cycles involves several methodological choices to be made. They are broken down here. We have first a choice between, are we doing attributional or consequential modeling? Are we trying to just track the impacts for our product or the consequences around it? And if we take the attributional perspective first, do we include or exclude the recycling process? Do we shift the recycling to the next user? That is one question to be answered first. And then we have this other question, the dependency between life cycles, because our present cycle, do we want to actually make them a chain of cycles in our modeling, or do we want them to be individually modeled and they are all independent? So this has to be taken into consideration. And finally, material quality. So like I said earlier, not all cycles will be equal if the materials degrade. So there's a way to reach our fairness between cycles, and material quality is one of them. And then we can move down to the consequential perspective, where actually, luckily for us, system expansion and substitution are very helpful because we don't really need to ask ourselves about the boundaries and the dependency between life cycles, because we will just expand the system all the way through, and this is the way forward for it. But we still end up with the material quality issue because shifting quality affects which material it may substitute. So in the long run, upcycling and downcycling of materials define why and how we recover our residues. Should it be considered as a waste, for example, if the material quality is too low, or how will the material perform in the next cycle? So what can be done with it afterwards is all dependent on the quality that we actually get out of it. So this brings us to the gaps that we're looking more in depth in this project. It's the quality is most often modeled through substitution factors. So this means that essentially when we want to talk about quality, we're implying a consequential perspective of our modeling. And then substitution factors are also, we double down because they are poorly justified. They are often one-to-one ratios. So this implies that if quality is going to vary just a little bit, but we just apply one-to-one ratios, we don't capture quality actually with most substitution factors. And there is currently no working model that exists in a attributional perspective for this integration of quality. So this leaves us wondering on our side at how important can integrating quality be when we're trying to resolve this multifunctionality. So as for the methods, we use the 5-step cascade of wood products. So first we go to forest, we harvest some round wood, we make some softwood lumber out of it, and we use it, for example, in a building. And then afterward, at the end of life of the building, we recover these planks. We turn them into recycled glue laminated timber beams. And these beams, again, have their own life cycle. And then afterwards, they're sent to become oriented strand boards. And again, particle boards. And at the very end, we burn them for energy. So this leaves us with a reference flow for attributional perspective of 1 cubic meter. So we're just following 1 cubic meter of softwood lumber, then 1 cubic meter of recycled glue laminated timber, and so on and so forth. And for energy valorization, we're going to follow 1 kilowatt hour of energy. And as for the consequential perspective, we will be cascading it. So instead, we will follow 1 cubic meter of softwood lumber. And then in the recycled glue laminated timber cycle, then due to recycling efficiencies, we'll be talking about 0.36 cubic meter of laminated timber that we'll be following. And now how we're going to make all our calculations, we're going to compare several approaches to allocation. So first off, we're going to use the cutoff approach, also known as 100-0. It's not that much the equation that is interesting, rather than this little diagram here, where the idea of the cutoff approach is just to actually separate our cycles. So each cycles are detached from one another. And we will also be comparing with the open loop that it has been brought up in the literature in 2016, where it's more about partitioning. So like this, like the diagram at the bottom, we take our cycles individually, but then we will use a partitioning factor to trickle down a part of our inventory. And then finally, we also propose an approach throughout the project. More explanations will come on this later, but essentially it is following the same idea that we could partition and trickle down our inventory to downstream cycles. When it comes to the consequential perspective, since we want to give this idea of quality, how it comes into play, we use the avoided burdens from Zink and Gehr in 2019, where not the equation is so much important as the diagram below. We have the blue box for softwood lumber and the downstream green boxes for cascading our wood products. And these steps obviously bring in consequences from system expansion and substitution. So the ones above, the dotted boxes above, are the direct products that they try to substitute. And below, since we're diverging recycled materials from being actually burned for energy, we need to actually bring in some unconstrained source of energy. So our marginal unconstrained source of energy for the province of Quebec in the long run is expected to be windmill energy. And now we get to the results. So we are comparing in the bands A, the cutoff approach, the bands B, the open loop, and the bands C, the proposed approach. So first in the bands A, we can see that the cutoff approach, we can use them as a form of a reference case because there is no trickling in there. So it's really just the emissions per cycle, and almost nothing else is different. So we can really take them as our reference. Then we move on to the results in the open loop. And first thing that is striking is the energy valorization, the black bands on top. So these bands actually are very high, and you can see that this does not happen with A or C results. And the main reason for this is because there is double counting. One of them is the first reason for double counting is because if we're going to start trickling our inventory, well, you need to take into account the reference flows, the functional units that you get out per cycle. And in this case, the open loop had nothing to actually take this into account, and this is what yielded double counting in the final step, because particle boards involve or somewhere around 400 to 500 kilograms of wood, but the energy valorization step for 1 kilowatt hour only requires a few kilograms. So this means that we're trickling down the inventory, but we're not taking into account that we don't need as much quantity in the final step, and we're overestimating our inventory for this one. And the other reason is how we are going to allocate our results. The open loop was actually reallocating impacts that were already allocated. So this is why we find double counting in there. And I hope by this time you realize why we actually proposed this, our approach, which is somewhat similar, but tries to go further by fixing this. And this is why you see that the energy valorization goes back to a very slim result that is hard to see actually, just like the cutoff approach. And the main takeaway that we have two important points for the proposed approach right now. First, in climate change, human health, and resource indicators, we get the lowest results, but not in the ecosystem quality indicator. And this is very interesting because the cutoff approach, by not actually trickling any inventory, will have a lot of impacts for going to the forest and harvesting trees on the ecosystem quality indicator. But then all the other subsequent cycles, since we're just recycling, we don't go back to harvest any more trees. This indicator is just very lowly affected by this. But the proposed approach, on the flip side, is fairly interesting, because since the first cycle is very damaging to this indicator, if you start consuming secondary materials that stem from this first cycle, you do not get burden-free secondary materials. So you will also get a feel that, well, we're not, you get impacts from previous cycles. And if you have a very impactful cycle in the middle or somewhere at the beginning of your system, you will know that you're consuming a material that has a previous background of being very damaging, which is not something you can see with the cutoff approach. Now, I said that this presentation was about actually the quality integration. So here it is. We actually used our proposed approach here, and we actually went into bringing in a partitioning factor that takes into account quality. And we made variations with bands A, quality is actually a void. We actually almost have waste. And we went all the way to a quality up ratio of 1.5. So we're actually upcycling our materials. And all of this can be compared to C results, because the bands C is actually our reference from previous slide. So what we can see here is that there are two things. The first thing is that our results for climate change, human health, and resources, the better the quality, well, the lower are the impacts, which is a very a nice thing, because we're expecting that if we're upcycling materials, then we should actually get the better results. And the second thing we can actually observe is that when we're changing the quality indicator in the around 1 to 0, or making this large variation to also 1.5, the overall influence is somewhere around 10 to 15%. So it's relatively not too harsh on the results. The influence over the full cascade is relatively limited. And now I want to move on to comparing attributional perspective and consequential perspectives, not exactly the results, but what they bring to the table. So we took, again, the bands A for the cutoff approach and the bands B for the proposed approach. And the interesting thing is that whenever we're using allocation, we should always converge to, if we sum them up, our allocated systems, they should always converge to the original value. And this is what we can see here. There is no issue of double counting, nothing is lost, and we're just adding up impacts in the attributional perspective to the same, with just different ratios. Then when we move to the avoided burdens, so the consequential perspective, then we are actually, since we are expanding the system, we can actually see that we have higher emissions, but also we're avoiding also far more emissions in most indicators. So climate change, ecosystem quality, and resources are actually found to be lower with the diamond markers. And we also have human health on the side, which has a very slight increase of like 2%. And the main takeaway here is that since the attributional perspective is just added up, we never get to see these benefits of recycling products, but we do see them when we move on to the consequential perspective with negative results. And now, again, the perspective of integrating quality to our modeling. So here we're using the substitution factor, and we're making it vary a wide range again. And in this case, we use, for example, the substitution factor D, 0 to 1.25, D equal to 1 being our reference from the previous slide. And what we can see is that there are large variations. We're talking about, for example, D from 1 to 0 in the ecosystem quality indicator is almost 130% of the result. And for the human health indicator, being the lowest variation, we're about 100% of the results. So this brings in this idea that actually, since quality is so closely tied to substitution factors, if we actually almost negate all the quality, then we end up with a situation where the consequential perspective is very influenced by the quality indicator. So in conclusion, this project showed that first, only consequential LCA could properly address environmental benefits. It's something that I do not want to go around it in the way that is very dear to me to bring this idea. And the next one is that quality in attributional perspective could influence results by 10 to 15%. Meanwhile, in consequential perspective, we're talking more about 97 to 138% per unit variation. And the main takeaway that I want to give for this presentation is that by integrating quality, it is 10 times more important in consequential LCA than in attributional LCA for this case study. So it answers our question at first. Well, how important is quality? Well, you should really look into it if you're going to do a consequential model. Not so much an attributional. It can still vary a little bit, but not as much as a consequential one. And before I go, I just want to say thank you to FP Innovation for helping us in building up the case study. It was a very insightful one, and we really enjoyed this project. Thank you.